All right, so we just talked about acidity across a row, but now we're going to do a group. So we'll look at, for an example, fluorine, chlorine, bromine, iodine. Those are all halogens in that group on the periodic table. And we're going to look at how the element impacts the acidity of those different atoms. And then we'll draw a trend from that. And this time the trend is really based on the size of the given atom. So the size controls the acidity. Okay, so again, let's just take a minute to practice our arrow pushing. So pause it for a minute, draw your arrows in for the proton transferring, draw the conjugate base and acid over here, and then think about the trend right here. Think about it for a little bit, form a hypothesis for yourself, and then restart the video, because if you're thinking through stuff yourself, it's going to make the material stick a little bit better. Okay, you've done that. We can show the protons transferring to our bases from our FH or our BRH. So that gives us F minus, our conjugate base, plus BH, our generic conjugate acid species. We can see the same thing here. Transferring our proton, we have Br minus and BH. Which of these was the stronger acid? Bromine is larger than fluorine, so what is the impact of that on the acid itself? And this really comes down, when we're thinking about the acid, to the bond strength. And what I said earlier when we were kind of doing an overview is that bond strength is correlated to bond length. So a longer bond equals a weaker bond. And a weaker bond is more likely to break. So if an acid has a longer bond, it's a weaker bond. It's a more acidic bond, so it's a stronger acid if it has a weaker bond. So how does that relate to bromine or fluorine? What we have to think about here is the bonds are going to be longer if the atoms are larger. So if we think about bromine hydrogen versus fluorine hydrogen, bromine is a heck of a lot larger, so we'll just put a Br there, than fluorine. So fluorine might be here. So a bond from the center of bromine out to a hydrogen here is going to be necessarily a much longer bond than the FH bond itself. So this is a longer bond and a weaker bond, which means that HBr is a stronger acid. What about the conjugate base? So this gets a little bit tricky for some people, because they want to go back to the electronegativity trend, because we're comparing Br minus versus F minus. And what people first go to is, well, fluorine is more electronegative than bromine. But what I really want you to think about is, well, what's the size of that? And what's the relative charge? So the charge is the same, right? We have a single negative charge here, we have a single negative charge here, but how much area is that charge spread over? Because charge itself is something that can make something unstable, but if it's delocalized over more space, that is going to make it more stable. So essentially, bromine having such a large atomic radius allows that negative charge to be spread out more widely, to be delocalized, and that's a stabilizing factor, whereas fluorine's negative charge is really localized in a very small area, and that makes it less stable. So this is a more stable, I don't think you can see there, it's a more stable conjugate base. More stable conjugate base comes from the stronger acid. We said that this is a longer, weaker bond. That's the stronger acid. So that's the trend. The lower you go with these atoms, the stronger they get as far as their acidity. Again, we can look at that with real pKa numbers. This was 3.1 as a pKa. We have -4 for HCl as we get bigger to bromine, -5.8. and -10.4. I don't have all of these memorized. I don't expect you to have them memorized, but I do expect you to understand that trend, and the trend that increasing size means we are increasing acidity. So that's how things work in a column, which a column on the periodic table is known as a group.